So today or this afternoon, what I want to do in the presentation is I want to give you a bit of an overview of probably quite a bit of my journey as into what I've been doing research-wise. So here and there I'm going to tap into and give you a bit more results, a bit more data, because I know there's people who like that. But overall, I'm trying to say where are we and where are we heading to, or where should we at least be looking to in the future. So in summary, or in short, we're going to have a look at what are our current computers. And I'm going to use an analogy to explain that, because I know there may be a variety of different backgrounds in this room. I'm going to look at the digital world in general, the components, the structure of what we've got, and then some of the trends of what we have seen over the last several decades, and why some of these trends should be worrying in a way, as into future direction then. I'm then going to touch on the topic big data. Most people have heard of big data. I'm going to do a very simple mathematical exercise here to kind of show that I kindly disagree with the fact that it's big data, but it's huge data. And we're not really dealing with it properly either. So there's a big challenge there. And then I'm going to start moving into the biological stuff. So where do we take our inspiration? How can we use some of that inspiration of biological systems? Why should we look at them? Why should we consider them? And how can we take that forward? And then we'll get into what is the next section, or what's the next part, and conclude. So currently, digital world, probably don't need to say too much about it, but it's all around us. Everything is becoming digital. And that goes from our very standard computers that everyone will know, all the way to standard appliances having digital control in them as well. So we are really living in a digital world, trying to digitize everything. And there's a few disadvantages of that, which we'll come across a bit later. But as for now, I'd like to leave you in the continuum of this being a perfect world. So where is all of this based from? And I want to go a bit back in history here, as in to see where digital comes from. Because if you really look where digital comes from, it was originally designed to do communication over noisy lines. And that's where we decided that it makes more sense if we go for something called ones and zeros. And in my case, I'm going to use those as black and white cars. And in our digital world, we use lots of those ones and zeros, so we get loads of those black and white cars, and we give them a meaning. So either they represent a number, or they start to represent text. And then we start to work with it. So we have text editing, we can do calculations, etc., etc. But effectively, the system was designed to do arithmetic and logic functionality, and that's largely what's been driving the sector, and that's largely also what it's been really good at doing. We have very fast computation who can do very quick arithmetic, numerical analysis, logic decisions, switching things on and off, automation, etc. Really brilliant at it. But the question is that good for everything that we need it for, and everything that we need it for in the future? Because we're trying to move along, right? So effectively, if we look at the structure of our current computers, you can identify three main parts. That's going to be your processor, your memory, and all of the communication between those. Yeah? And I'm going to draw this analogy forward as into with my cars, which means that if we're looking at processors, which for most people will be known as the AMDs and the Intels, and the Core i5s and i3s and i7s, and all of that moving along, and we've been mainly selling that with clock speeds up to a certain point that we then started to talk about dual cores and quad cores, etc., etc. Yeah? However, if we bring this back to our analogy, we're taking a bunch of cores of either being white to black, and we're taking them, combining them together, so it's like a garage, and we're producing a different set of cars. And at the end of the day, because we get loads of input and we don't need that much output, we also have something in excess, which turns out to be our heat. And that's one of the challenges that we've had a lot when it comes to silicon, is we get a bit too much heat, and so we have a struggle dissipating it. Yeah? But if we look at it implementation-wise, what we've done is we've gone from mechanical switches all the way to electronic switches, and then we just put millions of them onto one device. And these are our transistors being switched on and off. And what you see here is a die of, I think it's a Core i7 core, and you can very clearly see the different areas doing different parts, things which are very repetitive, like this, or your memory, or your caches, etc., etc. And you can kind of nearly reverse engineer most of this from the graphics itself. But that's not what we're here to do today. Now, second part is our memory. And in that sense, we've looked at two main parts. We've basically designed a hierarchy, but what would be known best to most people is our main memory. That's the working, operating memory. And then your more permanent storage. That's your hard drives, your SSDs these days, etc., etc. And we generically sell them based on the size, and especially also when it comes to main memory, to some extent on the speed that they operate at. But effectively, coming back to our analogy, memory is a parking lot. And it's a parking lot which is either short-term, which is when you're looking at your main memory, or it is long-term, when you're looking at your permanent storage. And so you can start to see that the size of my parking lot is the size of my memory, and how long I keep that data there is going to determine how long I store the data locally. So moving on to communication, and this is generalized because effectively you get loads of different standards here. I'm just picking on a few. That's Ethernet, USB, Thunderbolt, but obviously there's been loads of standards, and they come in and come out all the time, because what we're trying to do is we're trying to get this thing to go faster, and effectively all we're trying to do is to get our cars to move faster one way to the other. And we've done that in parallel, we've tried this in series, etc., etc. And you get some interesting pictures like this if you try to take the analogy forward. And this is, by the way, the M25 at night. So, now, in structure, what we've created is something like this. We've got a processor at the top, with a tiny bit of memory in there, which we call the cache. And then we've got various types of memory along the way, which we've built up in a hierarchy because it helped us to deal with things like costs, speed, etc., different trade-offs that we had. Now, as you can see in between these, we kind of get our communication channels, and that kind of means we kind of get like a bottleneck to go through. And that's also referred to by many as the von Neumann bottleneck. Now, it's a bit wrongly named to be the von Neumann bottleneck, because although it's part of his architecture, if you go back to original documents of von Neumann, he basically states, once you design my architecture and you take it forward into the future, can you please make sure that all of these three parts, processor, memory and communication, are developed at the same rate, otherwise you'll get trouble. That's a sentence that seems to have been overlooked, because what we've done is we focused on that top part, that processor. We didn't really care about the other parts, and then suddenly we've got a problem. Yeah. Now, the other thing to think about is this is a very deterministic system. It works exactly. It's either a white car or it's a black car. I don't have grey cars, I don't have red ones, I don't have brown ones, no other options. It's either white or it's black, and that's it. So this also has a number of consequences, as we'll see in a bit. Now, so if we're looking at the trends, and this is showing you where we come from, but also where we may be heading to in the future. So this is looking at a variety of different data, computer related, all the way from the 70s till about a few years ago, or a year and a half ago, depending on how you count. And we're looking at transistors, single-threaded performance, frequency, typical power, and the number of cores. Now, the interesting parts is, first of all, most of you will be old enough to remember that at some stage they stopped selling processors based on frequency, and they started selling them at the point of cores, and this is exactly around the point in time that you've got it here, around 2005, about a decade ago. Now, this line is still going up, depending on which article you believe, on Moore's law ending at some point. This is either going to end at some point soon or it's not going to end at some point soon. But we've seen those articles for a number of years, so I'll leave it to you to decide as to when it's going to happen. Do we have a problem there? Potentially. Let's keep it there, as for now. I think the more worrying part for me is if you start to look at all of these curves, they all start to go flat. So our continuous increase that we had several decades ago is gone. Yeah? And you can see that in practice, because at the end of the day, we're used to buy a new desktop machine every 3-4 years, several decades ago. These years, you don't need to. You know, your machine today is not better than the one 3 years ago. So why replace it? Yeah? Several decades ago, that was a significant improvement. So it was worth the investment. Now, it's no longer worth the investment. So what has the market done? Well, the market has done this. The market has shifted from desktop sales to mobile platform sales. Your smartphones, your tablets. And they managed to do this pretty well because they managed to convince most people for several years to buy a new smartphone or a new tablet every year. But even that starts to flatten out. And if you look at this, you kind of start to see the same trends. This is performance for these devices, and again, we're starting to go flat in all different ways. So we're losing things here. So the question is, where do we go from here? If we're trying to make a business out of this, where do we go from here? Now, that's not the only challenge. This one is actually slightly bigger. So the big data challenge has been around for quite a number of years. And there's, again, a variety of different success stories. But on overview, IT projects, including the ones as related to big data challenge, have a success rate of about 30%. Not that impressive. Yeah. Now, if you look at these numbers, you'll understand the reason as to why these big data challenges are actually pretty large challenges. So let's just look at what big data really stands for. Effectively, it's a broad term for data sets so large and complex that traditional data processing applications are inadequate. Now you can start the question here as in traditional processing applications. Does that mean our current computers, or does it not include our current computers? Again, I'll leave that to you to decide for now. But for most people in the streets, this means the data collection eagerness of companies like Google, and then that's probably where us engineers go like, no, I'm not giving you my data, because why should I give it to you? But on the other hand, there are benefits to this. For example, if you think about a doctor, as much as they train for a number of years, they obviously have to stay in a profession for even longer than that. They need to understand what is coming along. They need to continuously train. But that doesn't necessarily mean they will know all the little details of what they need to know. If you imagine a doctor in a small practice in some country like Hawaii, and he gets a patient coming in saying, I've got a problem, okay, I'll try to diagnose you, and he does a diagnosis, but he doesn't quite manage to, put the mark on what it really is. Yeah? There may be some research out in Spain, Germany, whoever, that has all the details that this doctor would need to know. But if you look at the current rate of publications, which is about a few million a year, you can't expect that doctor to have read all the publications, can you? So this is where data analysis tools can start to help, because these data analysis tools basically would take the data that the doctor enters into the system, as in, these are the symptoms, I think this may be XY, but then the system goes and says, hang on, don't you think that this is relevant? And basically starts to present this paper. Now this paper may also give indications as into which medicines to use, maybe medicine A or medicine B, but it could be a helpful tool in these kind of circumstances, because tools like this have access to information more easily than this doctor, because you can't expect him to have read about 2 million papers a year, in addition to also doing his practice. Yeah? So, how practical is our big data challenge? I'm taking a real life example that most of you will be familiar with, or have heard of at least, YouTube. YouTube is known to have statistically about 300 hours of video uploaded every single minute. So, and that's been like that for the last number of years. So it's been fairly stable. I'm assuming in this that this is stored in HD quality. I know it's not all the case, but let's assume it makes life slightly easier, and trust me, it's not throwing the figures off too much. So I'm rating this at 1 gigabyte per hour, so that means I get about 300 gigabytes per minute being uploaded. If I then take that over a day, that comes to about 432 terabytes. If I was to put that on 16 terabyte disks, which is about the biggest you can find these days, that gives me a pile of about that size per day. Just YouTube. Now, you'll start to see why I say just YouTube in a minute, because this 432 terabyte is only a small part of the 3 exabyte that we are generating and storing on a daily basis. So if I was to store that again in my 16 terabyte drives, that comes to about 5 cube per day. So that's about a small wardrobe. Can you imagine being sent out every day to buy yourself a small wardrobe to put all these hard drives in on a daily basis? Or in another measure, in the size of double-decker buses, it takes you a bit over half a month to fill up a double-decker bus at our current data rates. So per year that comes to a bit over a zettabyte, and to put a figure or a bit of understanding to that zettabyte, that's about 250 billion 2-hour DVDs. Not a single person on this planet who can ever watch all of that, right? So, now, it's even more worrying because our growth rate on this data generation is 60%. So by about 2020 we'll get to about 40 to 45 zettabytes, and it will continue to rise. Yeah? Now, if we take this forward, then we're trying to do something with this data, right? Because why would we store it? If we're not doing anything with it, you might as well chuck it away before you store it. So, I have created a hypothetical company which will look at YouTube videos. And so I'm creating about 432,000 hours of video per day. So if I employ people to look at YouTube videos for 8 hours a day, that means about 54,000 people. Approximately the size of Google now. Google is slightly smaller than that. Now, this has excluded sick leave, lunch breaks, all of that. And on top of that, these people haven't done any analysis yet. They've just watched these videos. Because if I want to get them to watch them, and I want them to put some information related to it, then I also need to give them some time to do the analysis, right? So it has to be a bit bigger than the 54,000, I'm sorry. But the more staggering part of this is that effectively YouTube is only about 0.0001% of all the data that we're generating. So you can easily get everyone out of unemployment tomorrow. Yeah? Now, it is no surprise probably then that currently less than 1% of that data is actually being analysed. Why? Because we simply haven't got the power to do it. And I'll tell you why this power is not there. Because here, looking at a power perspective, the current brain, the human brain, consumes about 20 watts. Again, depending on the source, you're going to get a slightly different figure there. if you were to use current technology, and then I mean your fastest processor, communication and memory available on the market, to develop something that tries to achieve what the human brain achieves, then again, depending on which source you believe, you will get a consumption of about, you will require a consumption of anything up from a few hundred kilowatts all the way to a gigawatt. And your machine is going to be about the size of a football field. Now let's not worry about the football field. What I want to worry about is the power consumption. What we've got in this table here is the biggest power generation stations on this planet as of a year ago. We've got the Three Gorges Dam in China, which produces about 22.5 gigawatt, or can produce about 22.5. It produces about half of that currently, so around 11. Yeah, it's a hydro station. So if I calculate this as in equivalent humans, because that's what I want to use as a measure for now, that's about 11 to 22 equivalent humans. I'm going to be jumping down now to the biggest nuclear power station, which is the one in Japan, which can deliver close to 8 gigawatt. And it currently delivers close to 7. So that's anywhere from 7 to maybe 70 equivalent humans. So if I calculate all of these together, I can't even get to the 54,000 people that I need, or 54,000 brains that I need to deal with YouTube, and YouTube was 0.0001% of all the data that we generate. Houston, we have a serious problem. So, why does it not work as well as we thought it would? So, well, first of all, we get loads of data. So, if we start to imagine all these zettabytes or exabytes or whatever of data, then we need to come back to this picture of cars. Can you start to see traffic jams? I can. Because there's loads of these things floating about. Now, all of these garages, our processors, they need to deal with this extremely efficiently. And any heat that we're wasting is pure waste. Yeah? If you can start to think about that computer taking about a gigawatt to process, and about half of that is going to be heat, it's not very efficient, is it? Yeah? Roads, well, roads are probably, if they're too narrow, too long, it's going to take too long to do that communication. When it comes to the parkings, well, I bet they can never be big enough in the circumstances. So we have a problem there. Now, why is that? If we look at the structure of our machines, then, as I said earlier, I started off earlier, we had the processor, memory, communication, and we've put a lot of focus on that processor, which kind of means now that we've put that system out of balance, because we only looked at one of the things and we never really bothered looking at the others until we noticed we had a problem. And now we're trying to catch up, but we're not quite getting there. On top of that, that processor is our central controlling unit, which means it needs to do everything. And if you've ever been in a situation where just one person needs to agree with everything, you're going to know you very quickly build up a bottleneck, because he needs to say yes and no to everything and initiate everything as well. Yeah? It works slightly better if you can start to distribute things, right? Well, this is not what we've got. We've got a centralized controller who needs to say yes to every single tiny little detail, otherwise it doesn't happen. Yeah? And that's also why we need this two-way communication to basically do the initiate, the response, etc., etc. Now, we've also separated everything into processor, memory, communication. The brain doesn't really tend to separate things that much, does it? So, why did we do that? Because if you think about it from a technological perspective, actually, we can bring things together. First of all, we can use memory to do processing, Anyone's heard of FPGA, reconfigurable devices? They got loads of lookup tables, which are effectively really tiny memories, and what you do is you put your truth table in there as data, and that's your processor. Job done. So I don't really need to separate those two. Additionally, and this is why the analogy kind of came in with the cars, your memory and communication don't really need to be separated. Because the only difference between the parking and the road is normally, and that's traffic jams excluded, the speed of the car, the speed of movement. That's the only difference, right? So if we start to think about things differently, can we get somewhere or not? Now, what we really need is we need some kind of architecture which is close to the human brain. It's got cognitive functionality. It uses an amount of power very similar to the human brain, preferably lower, maybe even a bit faster, but let's not dream too much. And so we need to, from where we are, we need to improve several orders of magnitude. We're not talking about a factor of 10, we're talking about factors of thousands and more. Yeah? We need to have a device which is fast and flexible, and we need to reach all of this as soon as possible because we continue to generate data. And as long as we keep generating it, if we ever want to use it, we'll need to be able to analyze it. So where does the biological inspiration come from? So you can look at a variety of different biological systems. And why do we look at biological systems? Well, biology seems to continuously evolve for the better. So there's probably hundreds of years of evolution and knowledge in biological systems which it may be useful to tap into and learn some of it and then see what we can take along when we're moving that over to developing our new technologies. But biological systems have certain characteristics, and I'm going to touch on a few. Swarm intelligence, which was probably hotter as a topic about a decade ago, but there's definitely lots of vibe around the human brain, and we'll see how useful some of that information will be. So swarm intelligence. Swarms, you've got a variety of different swarms. You can have them from bees, ants, birds, etc., etc. That's not really what we're going to look at. What we want to understand is, how do these swarms work? Well, if I was a bird in one of these swarms, then my task would be to keep the distance the same to every one of my neighbours, and that's the only task I've got. Unless I fly at the front, and then I'm responsible for direction. But other from that, I adjust my speed and location based on where everyone around me is moving. Yeah? So these things don't have a centralized controller. These things have very local communication and decentralized control. If we then look at, so what we've done here is we tried to basically sample some of this in something more practical. And we've taken an example study on something quite data intensive as an application, which is motion vector estimation. This is something which is standardly used, for example, in MPEG video coding. So if you're looking at digital television at home, or you're looking at DVDs, all of them have motion vector encoding in there. Why? Because you're effectively looking at the change between one frame and the next frame. And then you're just storing that change, and that's the only thing you send through. So you save a lot of data by doing that. So what we've done was we tried to build a few different approaches in doing this motion vector estimation. So if I want to do this motion vector estimation, I effectively got two frames. I take a small window out of one frame and I start to look in the other frame, where can I find this? So, and this where can I find this is not me as a human doing this, it's that numeric computer doing it. So effectively he will say, I'll try this, I'll try that, I'll try that, I'll try that. So he tries everything and then he says, oh, I think this is the best. Yeah. So there's a lot of computation happening before that decision is made. Very effective. Let's not discuss that for now, but this is the way it works as we've got with the platforms that we have. So we've built two different approaches. One is a heterogeneous one, where we had a central processor, and then we looked at the instructions on that processor, and the instruction that took up the most time, we said, okay, thank you very much, I will move you to reconfigurable hardware. So we did this on an FPGA. So you can move things over, and as soon as you put them on hardware, obviously they become faster, more efficient, etc. So there was another instruction that became more time intensive, and again we moved it off. And we did that a few times. And then the second approach was saying, okay, now let's just sit down and try and build something which is completely independent. A bit like my bird in that larger swarm, and simply can deal with the processing on its own. So on the heterogeneous approach, where we've got a processor, we started off with a simple NIOS processor, because this work dates a bit back, so it's a NIOS processor on one of the Altera devices. We then took the absolute difference calculation, which is where you do the comparison between the frames, off, put that on hardware. We then built a cell that dealt with the actual data processing, getting the data onto the chip, moving it on, etc. Off that, and then we built an external memory controller, so it is dealing with the control of these systems. Now, in this situation, we basically, you can see that the four different cases on the left-hand side. The clock rate is pretty much determined by the processors. That's why it's stuck at 50 Hz. And you can see that the area, so because I use a lot more hardware in the last case than in the first, obviously I'm starting to use more area. I'm also starting to store more data locally, so the memory increases, etc. But I can bring down the processing time per block to about half. So a reasonable improvement, but if I compare this versus the amount of area that I'm using, then I'm not really saving that much, right? So let's look at the hardware approach. What we did here is we built a controller that dealt with getting the data on chip, and then once it was on chip, we had a cell which basically dealt with looking in a specific area. So it dealt with the search for part of that video, and we could replicate these cells as many times as we wanted. They worked independently. If they were finished with a piece of data, they would move it on to the next one if it was still relevant, otherwise they wouldn't. Yeah? So it was a modular system that built up or structured very easily. Yeah? So easily scaled, etc. Now, if we then look at comparing, so we've got the results up there for the hardware, and then at the bottom here for comparing the two. If we're looking at the hardware-only approach, then at the top we've got a number of cells all the way from 1 to 5. And as you can see, the clock rate doesn't really get affected. The only thing that scales up pretty linearly is the area that we need, the amount of memory that we need. But you can also see that our time to deal with the whole thing scales down quite nicely and nearly linearly as well. If you then put these two aside, software approach, or let's say processor approach, versus pure hardware approach, then you can see that not only can we run this at about more than double the speed, we are using a fairly similar amount of area if you look at the simple case, but we can definitely process this way quicker. Yeah? So there is lessons to be learned here as to how we deal with processing exactly the same data, because what we're doing here is we're taking the same data and we're doing the same task. Yeah? It's just the way that we've designed it that's different. So unfortunately, these two bottom approaches, the hardware ones, are the ones where the designer needs to put more effort in. But it obviously pays back, time-wise, or in the actual performance. So let's have a quick look at the human brain as such then. If we're looking at the human brain, and you can then start to say, okay, does this fit with artificial intelligence? Yes and no, because I just want to be clear at this point, artificial intelligence as it is currently defined is not really intelligence to me, because the intelligence that we get in artificial intelligence is very limited. if I'm talking intelligence, I'm talking human brain kind of intelligence. I'm not talking artificial intelligence. So my aim here is really to get to human brain intelligence, not what we've got as artificial intelligence today. Yeah? So there is an extensive amount of work around the human brain. And we see loads of big projects. We've seen them in the States. They've been in Japan. We've now also got a huge human brain project in Europe. But a lot of them really focus on the bottom-up models. So we start from neurons, and we try to understand the neurons, and we try to build up from there. Now, one of the problems is we don't really understand how a neuron works, but we are trying to use whatever we understand to build a whole castle on it. For me, it doesn't make sense trying to build a castle on a foundation that's not really solid. But if they like to do it, fair enough. So that's why my approach starts top down. I like to look at understanding the human brain from a functional perspective. How does it work? How does it operate? And then what lessons can I draw from this? And then how do I map that to technology? Yeah? And we'll see some of that in the next slides. So, first a bit on neurons, just to get your brain washed. We're basically looking at a central cell body with loads of axons around it that receive signals, and then these signals are effectively looked at as pulses, and those pulses travel around. Those pulses have got meaning. What they are, we don't know, although actually we do, except for the fact that we all consider them to be digital. So the pulse is a 1 or a 0. Now why is that? Why is the pulse 1 or a 0? There could be way more information in that than a 1 or a 0, at least to me. Yeah. So, are we slightly biased by our digital world? Possibly. But we should probably look at that aspect as such. Secondly, the only thing that we really take from these neurons is the electrical signals. That's the pulse. But there are electromechanical signals, there's chemicals, there's loads of other signals flying around the brain as well. And we don't really look at those, we don't really consider them. So we basically say, well, it's only the electrical part that does all the job. No, it doesn't. Because your chemicals are based on your emotions, and do your emotions determine how you decide and how you think? Oh yes, they do. So why do we suddenly say, well, it's all electrical? Sorry, it isn't. Yeah. I know it complicates the figure, but you can't simply ignore things and then say it's not working at the end of the day. So in a large extent, we've got a lot of flexible routing as well, because all of these axons, these endpoints, as you kind of see up there, they kind of interconnect with various points, and those interconnections can change over time. So a lot of that routing is flexible. Now, a lot of this routing is also in what I call pure 3D. And I'll come back to that in a minute. So, if we're looking at artificial networks of these neurons, we've been trying to design them, and we've been simulating them quite a lot on current machines, but effectively, we don't really understand how the neuron works, and we are modeling a true 3D system into something that is a maximum of 2.5D, if not 2D. Because silicon, even stacked silicon, is not pure 3D. You are very limited as into the interconnections you can make. Yeah. Now, there are certain advantages to some of these from an applications perspective, like speech recognition and computer vision. Are we doing as well as the human brain? No, but are we doing pretty well? Well, we're doing all right. So, one of the other things to bring in as a slight deviation and bring it a bit more technical, memristors. Anyone ever heard of a memristor? Yeah, I see a few nods. For all the other people, your Electronics is, for a long time, has been based around the three basic components, which was your resistor, capacitor, inductor. Well, actually in the early 70s, someone called Leon Chua proposed there was a fourth element, and he called it the memristor. And so this fourth element has been produced, I think somewhere in 2008 in HP Labs. It was a bit of a surprise occurrence because they produced something which they didn't quite know what it was, and then they went to their boss and said, we've got something, we haven't got a clue what it is, and he said, well, it's probably a memristor, because he was the one who had read the paper. No one else had. So what are we looking at? Well, effectively our memristors give a relationship between flux and the other ones are going to escape me now at the key moment, but flux and charge. Yeah. So we can use them as analog and digital elements. We are obviously mainly using them as digital elements, while industry is currently mainly looking at them as a digital element to do memory storage, so to replace the technology that we're currently using in flash drives. There's a large potential in doing more with it. And from a research perspective, a lot of people look at them and say, well, actually they're very close to neurons. Hooray, we've got something. Yeah. What is very typical to them is the fact that they've got hysteresis loop. And this is a plot looking at current versus voltage for the device. Now, looking at the perspective top-down. If we're looking at things top-down, trying to understand the brain functionally, then, well, we learn through repetition and experience. That repetition doesn't always occur because you get things which just happen once and you've learned your lesson. You're never going to put your fingers in the plug twice, right? So there is a few exceptions to that rule, but generically we need repetition. And we tend to recognize patterns in space and in time. So in space we can recognize figures, images, objects. In time we can recognize music, and we probably don't need more than 3 seconds at the start of the song sometimes to recognize which song is coming up. Yeah? So we've got that ability to deal with these two patterns as in recognition. So there's other people who say, well, the brain is a massive associative memory. So you're looking for association. You're looking for something that you've seen before and that you've learned before. The easiest way to tell a non-convinced person why this is true is if I was to ask you, what did you do last week Friday at 3:30 p.m? I would imagine that most of you would struggle to answer that question, and you would probably say, can I look at my diary? Because maybe I can figure it out that way. Yeah. Well, the easier question is, what did you do the last time you went to the beach? Most people would be able to tell a complete story as into what happened the last time they went to the beach, even though that is probably longer ago than your last week Friday. Why? Because we store everything based on events, and so we build up the whole storyline. So we're not looking at individual dated timed items as into that happened at that specific point in time, which is again more typical to our current computer. You've saved this document at that date and that time, rather than the storyline that the brain seems to store. So what we did was we tried to build an associative memory using memristors, but then as an analog device rather than as a digital device. So we built two bridges. So we've got two cells, one on the left, one on the right. Effectively, these memristors have a polarity, so that's why you see the plus minus. And the difference between cell 1 and cell 2 lies in the fact that the middle one, so you've got left, middle, right, is swapped in polarity, effectively. And that means that we get slightly different behavior. So in the first case, left case, we can store two voltages, two separate different voltages. In the right case, we can store one voltage. One of them is positive, the other one's negative. Yeah, so we store the opposites. So what we did was we trained the system to look at a variety of different stored values, and then we provided an input, which is the thing here on the left, and then we saw whether it determined or it found the closest match. And it did. It did that in very nice conditions, so perfect conditions, but it also did it in noisy conditions, because this is where you see the noise at the bottom. So now I've got an analog system which is reasonably well when it comes to the noisy conditions, and let's be honest, one of the reasons we left analog was because it couldn't deal with noise, and digital could. Yeah? So if we try to find a system that works with noise, we may need to think about processing things in a slightly different way. Here's a few more graphs where we basically did analysis on noise at various stages, and that includes noise at the input as well as the learning. At the learning stage itself, and then as the recognition. Again, you can see all the noise as the small rumble at the bottom, and then the larger bars are the path where basically it says, here I am, this is the most similar value to what you're trying to do. Now, one of the challenges we had was doing this similarity detection. So we had our memory cells, which worked quite nice, could store quite a bit of nice values in them. But then we needed a lot of circuitry with very high precision op-amps to deal with the actual detection of this is the one. Yeah? And so it wasn't really beneficial. So we've tried to move on from there. Now, if we're looking at the system from a top-down perspective, I don't need to worry about storage, because storage is inherent in my system. I want a system that looks at similarity, and I want it to store or learn locally, yeah? And then do that exact similarity matching. I want to think about things like information density, because if I look at my digital world, my white and black cars, no, I need too many of those. I want information to be way more condensed when I work on it. And the similarity detection needs to be happening fast, and that for very large data sets, because that's what the brain seems to be doing. So what next? Well, let's just get an elephant out of the room first, because a lot of people say, what's next? Oh, there's quantum computing. Yes, there is quantum computing. Now, quantum computing works with something called a qubit, which is either a 0 or 1 or anything in between. That's why my car is split halfway. So, but effectively, it works completely on binary logic principles. If you dive a bit more into quantum, you'll probably understand that this is a serious limitation. And now one of the limitations that we've got here is, especially if we're trying to implement these things, is the thermal restrictions. Thermal energy influences our qubits, because they start to swap between the black and the white state, and that's not really what we want, because we want it to be either perfectly in one state and stay like that until we finish the processing. Yeah. Now, the other thing we've got is, as soon as we measure this thing, it's changed. Yeah, but it's one of the laws of quantum physics. So, as soon as you measure something, you're changing it. So let's learn to live with that. Well, yeah, we'll have to, because everything is coming to a quantum level. Even if we manage to continue our processors and our transistors to scale down, they're going to come to a level that they're an atom size big. Yeah? And then you definitely have to deal with quantum principles. If you don't believe with it being applicable at the large scale, it does apply at the small scale. Trust me. So we've got it coming up at some point soon. But I don't see it as a disadvantage. I really see it as an exciting opportunity, because quantum physics has a lot of things that are of interest. One of them is, well, it seems to explain quite a few things that we haven't managed to explain so far. So great. Yeah? Not really what I'm after, but one of the things which is really key, or could be key, in the processing context is I get two particles which are generated at the same point in time, at the same location, and they are entangled, which means they are like twin brothers. So if one changes, the other one changes. So how does that sound as a communication medium? It sounds perfect to me.
Synchronized.
Perfectly synchronized, and I don't need a wire. I can put them at any place, any distance apart, and I don't have a problem. And it gets even more interesting because most people then say, yes, but my communication is limited by the speed of light. Oops, no way. There's been tests done fairly recently, I think it was 2014 or 15, in Delft University, where they basically created these two entangled parts and then they separated them far enough into various university buildings. And what they did was they made a change to one of them, which then automatically would mean the other one changes as well. So what they did was they looked at the other one and saw when it changed, and they measured how quickly it changed. And then they did the calculation, distance times speed of light. Oops, this is going quicker than the speed of light. Interesting. Yeah. So it gets to very interesting situations, and it gets to interesting situations because I like these as twins. Look at how interlinked they are. One of them is being naughty, the other one is feeling really guilty about his brother. So, how do we get there? Well, I haven't got all the answers, but I think we need to explore a few things, and these are a few of them. First of all, we probably need to move away from things being purely deterministic. My brain up there is not deterministic. I'm pretty sure most of yours as well. We learn arithmetics. We are not born with arithmetics. Yeah? And we need to start thinking about a system that doesn't consist of one part and then another part and then another part, but consists holistically of something that works together. And I think the key part here is we need to think about the data. It's not about the processing. So, we need to find similarity. I've said that one so far. But we also need to look at differences. And why? Because the human brain is brilliant at spotting differences. While we focus with our eyes somewhere, we always have that peripheral vision. If something happens in the peripheral vision that may be a potential threat to me or my situation, I will immediately focus. That is a difference, that's a change, which I pick up instantly. Yeah? So, it's not about looking at one thing, it's looking at that and the opposite as well. So, we've done a quick test on some of this differencing scheme. And so what we did was we took a standard machine learning algorithm. I didn't really care what the machine learning algorithm was. I wanted to do something in addition to that. And what we did in addition to that was we added something in front of it which is called principal component analysis. And effectively what principal component analysis does is it looks at where each of these points are, where my data can be located, and then I am moving that data, or I'm grouping that data based on what's more similar. So my red dots are different from my green dots, or different from my blue dots. And so what I did was I took my data, I fed it into a machine learning algorithm, and then I looked at how good that worked. And I took the same data, put it into my principal component analysis tool, again into the same machine learning algorithm, but obviously it will learn differently. And then again I looked at how that system worked. And these are some of my results. My similarity detection, standard machine learning, around 50%. Doing a difference analysis before that, close to 80%. On top of that, I managed to save quite a bit of data because only 16% of all that data that was in my training set was unique. So I managed to save on storage space massively. Yeah. So you can see that just playing with this difference and similarity, I can achieve some interesting results. The other thing we need to think about is two-way processing. I don't want this wasted heat on the site. I effectively also want to go back. One of the reasons I want to go back is because I want to be able to deal with feedback. The brain deals with prediction. It predicts, and that's also one of the tricks it deals, or the way it deals with noise, because I make a prediction and I can eliminate some of my noisy input. Yeah? So this kind of throws another interesting one in here, is some people say the brain's got more feedback than feed forward. But we've never designed a system with more feedback than feed forward, have we? But if I want to get this to work, if I want to get this two-way processing to work, then I need to be able to move back to the original situation. So I need perfect two-way processing. One of the ways I'm gaining here is energy, because I no longer have that wasted stuff. So I really take everything that I've got, I just restructure it. That's all I do. So some of the benefits of this two-way processing is reversibility, energy balance, and I can improve on accuracy and reliability because I can start to predict, get rid of noise, etc., etc. So the puzzle itself is pretty big. The puzzle itself includes looking at how do I represent my data? If I don't use my white and black cars, how do I deal with it? How do I create any of this, even an electronic platform, when it comes to the similarity detection, doing it massively parallel, etc., etc. How do I deal with the quantum physics aspects of this? Because I'm going to be working probably at a very small scale. How do I deal with energy balances and energy efficiency? How does the system even learn? Can I use the existing machine learning tools that I've got, or do I need to come up with something different? What's the importance of feedback? And how do I implement it? And how, or what is the actual value of data? So if I start to look at machine learning, do I really need to store everything? Because that's what we do now. I don't think so. The brain doesn't store everything. We forget things. Yeah? How we forget things, I can't tell you, but we do. Yeah? We don't tend to store all the information. We don't tend to store all the details. But how do you make that the selection between what's important and what's a detail? Yeah? And get that done in technology, not by a human. So what are we working on today? Or basically as I speak, because most of my students are back in the lab now. Effectively, we're looking at things from a variety of different angles. And one of them is hardware related, so we're looking at hardware side. And that means how are we going to do that similarity detection, so the actual processing. But that actually links very closely to the actual data representation, how I represent the data or the information, and how I'm going to implement the system. You can draw exactly the same analysis for a digital system, and you'll see that binary, arithmetic, well, it's a deterministic system, I have no option. If I change one of those three, I get to a completely different system. Yeah? So, while we're doing this, we need to keep or be conscious of this triangle of interlinking, because if you change one of these factors, you automatically affect the other two. So it's quite important to get this right at the early stages, otherwise we're going down the wrong track. The other thing we're doing is we're looking at it from a machine learning perspective. So how can we deal with details? Getting rid of the details, getting rid of the non-important stuff, storing only the big lines, what we really need to know. How can we get a machine to understand what's important and what it knows and what it doesn't know? Because we humans, we know what we know and what we don't know. We don't necessarily admit it, that's a different story, but we know it. Yeah? The machine doesn't know that status. Yeah? So if you can bring a machine to that status, you can also get it to understand when it needs to learn something new and when it doesn't. So, in conclusion, if you ask my opinion, I think current computing is currently in the black and white stage, where similar to black and white televisions, we have a long way to travel to get to something good. If we're looking at biological systems, then they're definitely decentralized. There is no central processing unit at all. We have single cell types which are repeated over and over again. Look at your neuron structures and look at your swarms. It's the same structure repeated and that at various levels and at various scales. And so we've got loads of lessons that we can actually learn from biology to improve our thinking and get to intelligent systems. Now, I like to look at the world slightly differently because I think we need to. Just like this giraffe looks at this tree as a different opportunity, and I think that's what we need to do. So, just a quick thanks to my current PhD students. There's 4 up there. This is Christmas, a picture taken around Christmas. There's one of the, so there's only 3 students there besides me because one of them just started a few weeks ago and we haven't got a new picture yet. But there's obviously also various masters and undergraduate students who are working on a variety of different aspects in this long story. That leads me to the end of this, and so I want to thank you for your attention. And just before the microphone falls out, hopefully, I also want to move over to any questions.
Well, thank you very much, Wim, for the question and answers. Would you like to sit here or stand there?
Either works. I might need this.
And I think we might have a microphone to pass around, or somebody has.
Is one on there?
They offered one, but maybe we need to ask it louder. He's coming with a microphone, but meantime I see Gary's hand is waving around.
Right.
So shall I come to you first of all? Yeah.
Hi, Gary Hayes.
Hi.
Feed forward, feed back.
Hmm?
That was an interesting slide, but not really descriptive. Could you elucidate?
Okay, so in generic, the question is feed forward, feed back. It was a very generic slide. Can you get into more detail? What we're looking at is we're trying to, for us currently, the feedback mechanism is part of dealing with the noise. And so I see it as, if you start to think about a network that is effectively learning. So you've got a repetitive structure of cells which learn, and also see these cells probably to be hierarchical in a way because you need to come to a decision at some point. But that also means that in this layered hierarchy, you are looking at a variety of different levels of abstraction of information at those different levels. So while the sensory input comes at the bottom and is very detailed, as a move up, I move up in abstraction. Now, if that sensory input is noisy, I may get an impression of what I'm looking for, but I may not necessarily have the right answer. However, I may, at the first level, I may say, it looks like, yeah? And so the second level, who may obviously brings together information from a variety of different areas, may say, well, actually, I think it may be this, and maybe feeding this back as a prediction. So your bottom layer will then compare and say, okay, is this possibly a noisy input or is it not? How to do it in practice, as into the real life system, is still an interesting challenge to be looked at. We are currently in that context of thinking at a more systematic theoretical level as into how do we get the feedback in there, what's the benefit of the feedback, and how are we going to use it effectively in this two-way processing model. How to do it physically, I will maybe tell you in a few years, or more, I don't know.
John has got the microphone, so I think if you
Questions of the...
Hello. Hi, Andrew Sastos. So one of the useful parts about computing of today are operating systems that let ordinary people use computers without having to know how they work or without being electronic engineers. What do operating systems look like for biological systems?
Right. Personally, and let me make this point clear, I don't think there's any need to get rid of what we've got. Yeah, it does a lot of tasks really well. Yeah, So there is no need to replace it unless it's going to be a million times better. Which I'm not predicting this to be on an arithmetic platform. This is not going to be good at arithmetic. That's not what I'm aiming at. I'm aiming at cognitive functionality, which is a quite different task. In that context, I don't really see an operating system as in the current world as well. I see a system that's basically learned a particular set of tasks, and hopefully a system that can also improve itself as you progress. When you do that, you start to get interesting challenges as into, well, when it becomes malicious, or if it learns the wrong thing, how do I get rid of it? And so there's a lot of interesting questions in that area and how you deal with it. But one of the aims of doing what we're doing by looking at the hardware side as well as the software side and trying to bring everything together, while also thinking about how do you represent that information, how do you deal with it, is so it's working at these various levels but also from different angles, is that we're aiming to get that system to be understandable to us humans. Because one of the challenges with current machine learning tools is they're pretty much a black box. You put stuff in, you get stuff out. And when it comes out, you're kind of praying, it's the right thing or it's not the right thing. But they're effectively not reliable because you can have two systems which are designed identically, you train them identically, but they may behave differently. And no one can tell you why. Why? Because we don't know the content of the box. So our aim is really to understand the content of that box, so I have control over what's in that box, and therefore I can make a repetitive system which is reliable. So if I make this off a manufacturing line, I can say this is going to work this way, in these circumstances.
Brunella Long, I'm a consultant. I was wondering two things. One, pretty technical, the other possibly a bit of a vision forward. And the first is, why all these machine learning developments are trusting inference-based processing, whereas it's pretty much clear that there is no intelligence in inference process, or what you get is exactly what you put in. So there are margins of errors enormous. So I ask myself where this fascination for inference comes from, because I remember in my late 80s, first 90s university studies about artificial intelligence and information retrieval, there was no such fascination for inference. There were a lot of underlying doubts about the effective potential of artificial intelligence based on inference. And so I ask, where does the fascination come from? The second thing is, why do we need biological systems to exercise a creative thinking about computational intelligence? Why don't you think, for instance, well, you as well as we, why don't we think about a geological system as a metaphor for new computational models? Seems pretty much simpler, layer-based, with a diachronical way of computing stuff. I don't know, is anybody thinking about alternatives models different from biological?
Okay.
The answer.
To answer the question, the first part first, as into inference and machine learning, I think I don't consider myself a pure expert on machine learning. As such, my background is mainly hardware. But I think the important question there is as into, why has it changed from where we are to, you know, why is that drive to what we're doing now different, right? I think the drive for this is probably because, you know, if you look at the big data challenge, we've got data analysis to do, and there's only so many things you can do in a statistical context. Yeah. So people are probably interested in finding tools to deliver that. There's obviously other applications like autonomous cars, and so there's interesting challenges there. Just to name one of them is the trolley challenge. People who haven't heard about it, if the car is in a situation where there is going to be a fatality, the question is which one. Yeah. So how does it make that choice between which fatality to go for? If you think about a logical system trying to make that decision, that means that that system needs to fully be programmed for every single possible situation that's ever going to occur to make the right decision, if there is even a right decision in that context. Okay? So are we going to deliver a system that's ethically accepted in our context? Because you're talking about ethics here as well. Yeah? And I think a lot of discussion around ethics is still to be had in this context, and needs to happen now rather than later. So why is that drive? I think, you know, industry is to a large extent looking for something new. The car industry wants to get autonomous cars on the market. They say we're going to do it anyway, even if technology is not quite there, if I can say it that way, because they need to sell their new cars. It's a money-driven industry. Are we going to get the right technology on the market first time round? Probably not. So how are we going to deal with that? You know, there's quite some interesting challenges there. Coming to the second point, as into why are we looking at biology and not geology? For me, and I didn't really go into this in detail, but if you look at the basics, principles that apply to biology, you can find them anywhere around in nature. For me, that would also mean geology. So if you, and just to know, without wanting to blow anyone away with the term, if you've ever heard of fractals, and you start to look into what fractals are and how they operate, fractals are effectively a repetitive structure that repeats itself as a pattern, but it does that at various levels and various scales. So it starts from a very small scale, but it builds up to a very large scale. And so fractals are actually very typically found back in nature and in biology. And so fractals are one of the things we are looking at to understand how you build that structure repetitively. Because if you want to build a system like this, which is structured around a cell, you need to understand how that small cell works, but then also how that replicates and how it builds up to a bigger system, because otherwise you're not getting there. So there's a variety of different things to be considered, but yes, I do agree. There's geological is for me in the bigger term of biological as well.
But to comment, if I could interject some thoughts, that biological systems represent at least an existence proof that you can do this sort of thing, because we look around, we see what they can do. We know they can do it. On the other hand, we also know it took millions of years for them to evolve into the state where they do the things they have.
Yep.
So, I sort of wonder, are we trying to jump the gun by doing this within 1 or 2 lifetimes? Is this just impractical? Maybe there's no answer to that. But we can take 1 or 2 more questions. I see one there, and then I see, looks like Martin.
Well, John is moving around. I would say in that context, because biology continues to evolve, even if we look at what we've got now and try to replicate that, probably by the time we've replicated it, it's moved on already. So it's going to continue to be a catch-up game.
Let's take Don first.
Yes.
I'll save my legs, Tony.
Yeah.
That's all right. Should we take
It's
Don
good
first?
exercise.
You can, one way or the other. Fight for it after.
Since we're in the West End, I was thinking of Great Newport Street earlier, but I had to actually look at the map. The moment I looked on the map, there it is.
I remembered the name. You were saying how we forget things. Now, with data systems, if my bank forgets my data, I'd be very upset.
I can imagine.
Well, unless I'm overdrawn, in which case that's another story. I think we remember more than we realise. What occurred to me just then was, in context of this talk, was the information is actually there, it's buried, and as we get older it gets more and more buried. Is that because of the fact we actually have more information to handle, or what's actually happening to this information? Do we know? And how would we replicate that or otherwise in a quasi-biological system?
I think we've got a rough understanding of how some of that goes. I'm not a psychologist, so I'm not going to, or a cognitive psychologist. But I think what happens is you've got, so effectively, we've got a day-night cycle, and a night cycle relates to the fact that we go through the data that we've gathered that day, and we process what we need to keep long-term. So that's where our storage effectively happens, or storage into long-term memory happens at night, and that's why sleep is important. So how it processes, or how these things change over years, obviously I think it's a bit like, I'm going to draw an analogy which I don't like to draw really, but it's going to make life slightly easier. I think what happens is the things that you seem to make use of most are closer or in your main memory. The other stuff ends up moving to the back, yeah? And the more it moves to the back, you know, possibly challenging, or more challenging it becomes to pull it back out again, but that doesn't mean it's forgotten, yeah? So you can come back and you can practice and analyse that.
Association. Had it not said Great Newport Street on the map, I'd still have known. Somehow or other that was tied in with something else, so there is a link there. Exactly.
But that's the thing, it's in that context of associative memory, all of this information is interlinked. Yeah? So, and that's where one of the challenges comes in when you start to look at, okay, how do I represent my data, and in which and how many dimensions can it interlink with one another? You need to get that as an understanding, because there's various ways you can get to that same point. Effectively, it's the routes you take rather than the actual destination nearly. So there is a lot of interlinking.
Are we going to move more towards the relational database, or further from it? Or will this be a different form of
I would imagine we are going to move more towards relational information, because that's where some of this analysis and power really will come from. Yeah.
Can we move on to Don, and then I think that's going to be the last question.
Don Swift Hook. If you want to know who to vote for in the election that's coming up for trustees, there's a list of 9 people.
Guess what?
I recommend you to look down the list. Sorry, that's by the way. You gave us the idea of how to handle large data, and by implication, those techniques are not really appropriate for small data because they'd be wasteful and inefficient and so on. And it's an interesting question, how large do you have to be large data? But that's not the question I wanted to ask, because it seems to me that when you talk about biological systems, you almost automatically think of very large systems. And my question is, those techniques that you use for these large biological systems, how small could a biological system be and still use these biological techniques? Are there really seriously small biological systems that still work the same way? Do you follow me? In which case, your biological techniques might work not just for large data, but for all data, small, medium and large. Is that a sensible question?
That is a sensible question, yeah. So I think to give an answer to that, I'm going to come back actually partially to, if you're looking at fractals and the fact that is a lot of the structure of biology repeats itself at various scales. You will see that, you know, some of that architecture, if I can call it, has a repetition within it. So what happens at
triangle thing and show
to some extent, yeah, that wasn't really a fractal, but there's, I think I've shown once a letter automata, which is a special case of fractals. But there is, so I think if you look at biological systems, depending on, let's say, scale of evolution, from a single cell organism to, let's take ourselves as humans, there's probably differences there, right? The single cell organism probably doesn't manage to speak and communicate as we do, but it doesn't mean that it doesn't communicate, right? It may communicate in a different manner. Yeah? So, are there lessons to be learned, or can we scale the system up and down? I would think we can. I personally, at this stage, prefer to start at the larger system and dealing with the larger data sets, because that's where the challenge lies. Is your aim to get the system to do arithmetic? Not really, but if I got the system, I'm going to try it and see whether it can do it. So, can you scale it down then? Oh yeah, why not? I mean, ideally, and I don't know at what stage this will happen, and I've got my phone on me, but you want a device which is the size of your phone, which delivers your cognitive support in a way. That's what you want. And that's going to have to interact with, you know, the existing systems that we've got. But that would be my ultimate game. You know, if that's my goal for life, we'll see. But this is the direction to move on. So I do believe in scalability, and I do believe in the fact that we may be able to scale this up and down. But that also means that we need to kind of get this right as into how we deal with it. So how do we, you know, build it up from the smaller cell to the bigger thing, and then how can we start to scale it?
We should let Wim off the hook now, if that's the right word. And could I call on Alan for our vote of thanks?
Just before Alan gives the vote of thanks, if anybody has snake team, I know there's one, please sign the register. You've heard me say that so many times. I apologise for keep on repeating it, but it is important. Thank you.
Ladies and gentlemen, Wim, I spent most of my career in the Biotechnology and Biological Sciences Research Council, and in that we were trying to simulate with computers biological systems. I'm glad to say that I retired while we were trying to find out why piglets, or how piglets recognised each other. We had a postdoc who was trying to do a programme on it at the time. I'm also a bit of a dinosaur. I still have a Brunswiga calculating machine in my loft where you wind the handle and it adds up. So I approach data processing with trepidation, nay, terror. And I was so pleased when Wim led us through with the car analogy, which was a great help to me, I can say, and then into the size of data. Now that was a revelation. The percentage of YouTube, for instance, how small a percentage it is. Now, I don't know who of you were here for a talk last year given by a young lady from UCL who was mining data. It was tweets and Google lookups of flu epidemics and so on, so that you could predict the incidence. She was sort of ahead of the curve by about 5 days with an epidemic by doing this.
And they got it wrong.
Well, there's.
They got it up to
What that even makes the point that the amount of data that was trying to be handled is incredible, and you have explained how difficult it is to do that, and ways in which we can possibly overcome it. I take the New Scientist, and I've been following all this quantum computing and things, and Alice and Bob and entanglement, and I find the whole talk really brought it home and really explained it, and I wish you every success. And can you all please join me in thanking Wim for a most excellent talk.
I think you all know that if you go out into the Faraday Centre, you can sit in comfort and talk to people, and you might even be able to get another question in if you feel a great urge. Again, thank you all for coming. Thank you for being a good audience. And remember, this is the last of these events. We plan to have more roughly monthly talk ones in the future. We'll making us do it. So thank you again for coming, and I'll perhaps see some of you around later. Bye.
For those who want to sneak out and not really talk to me but prefer email, there's business cards on either side. There's some on the table in here. Feel free to grab one. Yes.